good afternoon, everybody. I hope all of you are physically and mentally well and taking care of yourself and each other. Today, our guest is Ms. Marialis Rosario-Franco. She has a bachelor's degree in applied physics from the University of Puerto Rico, and she's a PhD student from the University of Texas in the US. Today, Ms. Marialis will give a talk on orbital stability studies of exons and applications to exomoon candidates. So please, Marialis, you can start your presentation.
Thank you. I appreciate that introduction. It's great to be here. I am, as was said, I am a PhD candidate at UT Arlington, and I am also a Raber Fellow at the National Radio Astronomy Observatory at NRAO. And I am excited to talk to you about orbital stability of extrasolar satellites and application of those constraints to different candidates. And so overall, this is a bit of an overview. I will be going through a bit of an introduction where I will be defining some concepts and giving you an update on the status of these concepts in the field. Then I will talk about my work, determining these constraints and orbital stability studies for exomoons and submoons. Then I will talk about the detection thresholds for these satellites. And then I'll talk about a little bit about a collaboration that sparked from that previous work where we apply the constraints I was able to draw to different exomoon candidates. So before I move on, I would like to make a distinction between several terms that I will be continuously using throughout this talk. I will be referring to moons as the natural satellites that orbit planets. I will be referring to exomoons or satellites as natural satellites that orbit exoplanets. And I will also be referring to submoons as subsatellites, which are the moons of moons. So essentially a natural satellite orbiting another natural satellite. So far with moons within our solar system, we have 193, where 185 orbit planets and 8 orbit dwarf planets. And so we only have 2 planets in our solar system that do not host natural satellites. So we can make a fair assumption that moons are quite common. So we can also think that because moons are so common in our system, they might be common in exoplanetary systems, and that is where the term exomoon comes from. And so far, there are no confirmed detections. Several methods have been proposed, most of them derived from previous detection methods with exoplanets. Among those methods, there is one I am heavily involved with, and I will make a bit of a segue to talk about that because it's a big motivation behind my project with orbital stability. And one of those methods is radio detection. The radio detection method is based on an interaction that we see between Jupiter and Io, where Io in its orbit tries to, not tries to co-rotate. Actually, there is a plasma torus that comes from Io's highly volcanic activity. And this plasma torus tries to co-rotate with Jupiter's magnetic field. So there is a difference in velocity between the orbit of Io and this plasma torus. And then this difference in velocity gives rise to unipolar induction, where electrons are inducted into Jupiter's magnetic field lines, and these electrons travel through these field lines and create a current. This current, once it reaches the pole of Jupiter emits a very characteristic radio emission. And so the way Noyola in 2015, who proposed this, approaches this is, if this happens in our solar system, could it happen outside our solar system? And could we use this to detect exomoons? So following up with what he had proposed, I am currently conducting exomoon searches with 2 different radio telescopes. We have data from the Giant Meter Wave Radio Telescope in the left panel, located in India. And we have been approved for around 300 hours of observations with the long wavelength array located here in New Mexico. And that is the telescope that you can see in the panel to the right. More specifically, we are after very particular emissions. And what I am showing now is the dynamic spectrum that we recover from the Jupiter Io emission. And this dynamic spectra is very particular. It is characterized by having these arcs that happen in a specific amount of time. And these emissions can be very dim if the planet is situated far away. That is one of the main challenges of this detection method. However, they are boosted. We see within Jupiter and Io S bursts and L bursts. And so when these occur, they are so bright that they illuminate our solar system in such a way that it becomes brighter. This emission becomes brighter in the radio wavelength than even the sun. So although if this were to happen in an exoplanetary system, considering that this burst can occur, and although if it happens in an exoplanetary system, it's likely to be dim, if these bursts occur, then this could be very detectable. And why do we care about this from a dynamic point of view? Well, here we can see IOB, IOD, IOA. These are very specific, and IOC, yeah. These are very specific dynamic spectrum that depend on the phase of Io around Jupiter. So essentially, wherever Io is in its orbit around Jupiter will produce a different emission. Therefore, in my thesis, I propose to use dynamical studies to identify best observational candidates that could make these emissions. And this is a big motivation for my dynamical work. Other proposed detection methods for exomoons, as I said, are derived from observational methods for exoplanets. And one really big one is transits. And actually, this method has given the field the very first candidate for an exomoon that was put forward by Tichy and Keeping in 2018. And that is Kepler 1625b, where the system is a Jupiter-like planet that might have a Neptune-sized moon around it. And so essentially it was discovered through several studies of orbits and, several studies of transits, and that includes transit timing variation. I have to emphasize that transit timing variation is not enough to consider this a candidate. It needs to be confirmed over and over. And these were further confirmed a year after it was presented as a candidate. Not confirmed, but it went through a rigorous process to be presented as a candidate. And by that, I mean not only Kepler data, but also follow-up observations with Hubble were necessary in order to put this system forward as a candidate. So we've talked about moons, we've talked about exomoons. What about submoons? Well, submoons were originally put forward, and that term was originally coined recently by Kohlmeier and Raymond, where they presented some analytical studies, which I will talk about soon. However, no such configuration is known in nature. There are two possible natural instances with Rhea and Iapetus, where with Rhea, it's been argued that the debris that orbits it is the product of the decomposition of a possible submoon that just came too close, reached the Roche radius, and disintegrated. And now it's just that debris going around. So that's a possibility. Another possible instance that has been argued is Iapetus equatorial ridge, which was observed by Cassini in 2007. And so it's also been argued that that is the product of a pre-existing submoon that was lost during migration processes or tidal migration processes eventually. There is no way to confirm whether these possible instances are in fact true or not. However, I just thought it'd be worth mentioning that this has been argued within our own solar system. So, submoons, more on that. Could a moon possess a moon itself? This is a question that Kohlmeier and Raymond asked themselves, and they used an analytical approach to obtain the parameter space in which a moon of a specified planet could host a submoon under the action of planet, moon, and submoon tides. Specifically, they derived the necessary radius for a moon to host a long-lived submoon. And they do this based on an equation that was introduced by Barnes and O'Brien. So essentially, Kohlmeier and Raymond introduced an analytical expression for the radius of the moon, and they based their analysis on both Barnes and O'Brien and Domingos et al. 2016. There it is. And here we can see that Barnes and O'Brien derived an analytical expression for the mass of the satellite to survive the tides, whereas Domingos et al. Essentially derives expression for the same major axis of a prograde or a retrograde satellite. I must emphasize that both these expressions depend on prior estimates of stability limits, and they use a scaling factor F, which is the fraction of the Hill radius. And these are typically used. And they're analytical, yes, and so, sorry. They show an outer stability limit for submoons, right? And so they show that not just any moon could host submoons. More specifically, I also have to emphasize that for these Fs, these fractions of the Hill radius, there are different values to it. So for their work, they use an F of 0.49. So about 50% of the hill radius, whereas Barnes and O'Brien, which they based their expression on, uses 0.36. And Domingos et al. has a fraction of the hill radius that is more similar to what they use. So even though they derived the expression from Barnes and O'Brien, they use the fraction introduced by Domingos et al. So motivated by this, I decided to further this analytical approach into a numerical one and see really what are the conditions necessary for Kepler 1625b to hold a submoon. Specifically, I focus on the prograde case because I am not necessarily considering a capture situation, whereas retrograde cases are mostly associated with capture cases information. So I aim to derive an expression of the critical semimajor axis for a prograde orbit for both exomoons and submoons. So in order to achieve these, I did some orbital integrations, and this is my initial setup where the parameters of the star and the planet are derived from Kipping 2009, and the parameters of the submoon are derived from Kohlmeier and Raymond. And very specifically, given the restrictions of the system, I obtained a mass of submoon that is about 70% of Vesta's mass, and a radius as well. So we essentially use Kohlmeier and Raymond to determine the parameters of the submoon, and we use the observed parameters for the planet and the star. And so what we see here on the left is the setup of my simulations. What I have here in panel A is the sun, or a sun-like star, and a Jupiter-like planet, which is in red. And around that Jupiter-like planet, we have the proposed exomoon based on Kepler. So in panel B, we have a zoomed-in image where we have Jupiter in the center, and we have the exomoon Kepler 1625b I around it. And in panel C, we have more specifically the regions around the moon that we explored for the possibility of a submoon. I really want to mention that the only thing that is to scale here is the size of the orbits, not the radius of these objects. The radius of these objects are not to scale. They've been made bigger so that you can see kind of the setup. For a better representation, here I have kind of what I mean. And in the bigger panel, we have the star and both the satellite system orbiting the planet. And then in the lower left, we have the planet, the host planet. In blue, we have the exomoon, the proposed exomoon, and in black, we have what we would consider the submoon. So how did these integrations came to be? we ran two sets of integrations. One set of short-term integrations and one set of long-term integrations. For the short term, we used Rebound, particularly the IIS-15 integrator. And we explore a region of the semi-major axis of 0.05 to 0.55 of the Hill radius of the satellite. And the initial conditions are listed below. And specifically, we care about the time step so that it's small enough to be able to observe the movement of these submoons. And then for the long-term integrations, we did 10 million years using Mercury 6. It's a modified version of Mercury 6 that allows us to switch between Berlish-Stoer, the Berlish-Stoer pattern to Wisdom-Holman. And so it allows us to use one for submoons and one to evaluate the planet and the moon. And so the reason we do this is because initially we did the short-term simulations and we saw a truncation around the black area that we see here. We saw that most submoons kind of stayed in that black area and fell there. So we wanted to explore more about how submoons would survive in that area. And we ran our simulation for longer. And once we knew that that was kind of like the sweet spot in the phase space, that's where we took the liberty to run longer simulations and also vary different things. So essentially, in our first short-term simulation, we didn't vary many parameters. However, in the long-term simulation, we did vary several parameters. So more specifically, we have the eccentricity and the inclination were taken at random with a Rayleigh distribution. And the rest of the parameters specifically were taken from uniform distribution. And so with both of these, we aim to assess both exomoon stability and submoon stability. So for exomoon stability, we varied the initial mean anomaly, the semi-major axis, and the eccentricity of the planet versus the mean anomaly and the semi-major axis of the satellite. And then for the submoon stability, we varied the mean anomaly and the semi-major axis of the submoon with respect to the eccentricity of the satellite. Why do we care about varying mean anomaly or having different initial phases? This has a lot to do with my motivation behind pursuing these dynamical studies from an observational point of view, and it has very much to do with a previous paper that was put forward by my collaborator, Billy Quarles, who is the second author of these studies, where he identified that a change in initial mean motion or mean anomaly will have a big impact on the stability of exoplanets within binary systems. So because this is a similar four-body problem, we believe that this is something that we can improve on or we believe back then this could be something we can improve on previous known limits for satellites. So it's just essentially considering an extra variable that wasn't considered before. And so we recover coefficients for the expression of the critical semi-major axis for both exomoons and submoons. And these are the results here in the right panel. At the top, we have the critical semi-major axis of the satellite with respect to the planetary eccentricity. And at the bottom, we have the critical semi-major axis of the subsatellite or the submoon with respect to the eccentricity of the planet. So to be more specific here, these little, these small squares that we have, these small squares that we have represent the initial main anomalies and at what times or where in the Hill radius they stop being stable, and the black region represents where there is stability. We compare our results to previous work done for satellites, and we see that our exomoon F, or the fraction of the hills of the Hill radius where these exomoons are stable, is 0.4%. And for submoons, that is 0.33%. And please remember that when we're talking about these Fs for the moon or the exomoon, we are referring to the Hill radius of the host. So the host of the exomoon is the planet. So it will be 0.4 of the host planet, of the Hill radius of the host planet. And for subsatellites is the Hill radius of the satellite. Before I move on, I would like to point out that we compare this to the previous work done by Domingos, but this had never been done for submoons. So we introduce this expression for submoons. Taking it a little bit further, we are aware that this stability that we have drawn will highly depend on the tidal evolution of this system. And so we decided to take a bit of a step further and apply tidal constraints. We base these constraints on Barnes and O'Brien, and we evaluate satellite migration. More specifically, we assume tidal love numbers. And so we assume the tidal love number for the planet to be Jupiter-like. And we also assume the tidal love number for the satellite to be Neptune-like. And so what we see here, the top panels are these constraints applied to both satellite mass and planet radius. And so we see the values of these constraints vary depending on the tidal quality number, which is Q. So we consider different tidal quality numbers, and depending on these tidal quality numbers, we find different tidal constraints. In the gray region here is where everything is stable, independent of the tidal quality number. And at the top panels, we can see the star representing where Kepler 1625 BI would fall. We do the same for submoons, but because there hasn't been an observed submoon, we can't really set where our system would fall. These are just different possibilities considering different cues and considering this specifically, this specific love numbers. So, can we observe or detect these satellites? We know they can be stable. We know under which conditions they can be stable. And we know not only the orbital stability, but also we know how this stability can change considering tidal constraints depending on the tidal quality numbers. Well, taking it further in our paper, we evaluate the possibility of detection for both exomoons, which has been evaluated before, and submoons for different detection methods, specifically 3: radial velocity, transit method, and obviously the method I'm interested in, which is radio detection. Even though these detection methods have been assessed for exomoons before, I think it's important to reassess them, and not just reassess them, but compare these with what would happen if there was an submoon there. The reason is most of these detection methods are based on perturbers, on an emission or a signal that we are receiving on Earth, and we see a certain perturbation, a certain shift, like it's the case with RVs, like it's the case with transits and transit timing variations, etc. So for RVs, we perform separate numerical simulations. We performed a numerical simulation that was only star-planet, one that was planet-satellite, and one that was satellite-submoon, and then one that encompassed everything but the star. And so we see a difference of around 8 meters per second in the stellar reflex motion, and 150 meters per second in the planetary reflex motion produced by the presence of the exomoon. So this is what we can see in both panels on the left, where at the top we address the stellar reflex motion. At the bottom we address the planetary reflex motion. And for the top, we have in red the stellar reflex motion due to the presence of the planet only. And on black, we see the reflex motion due to the presence of both the planet and the satellite. And what we can see is that there is definitely a difference. And we can tell that there is a presence of a moon there. It is measurable, it is small, but it is measurable. Now at the bottom, we address the planetary reflex motion with the presence of just the satellite. And what we can see, though, is that, what we can see in the reflex velocity there is that definitely it contributes. But when we move on to the reflex velocity of the exomoon due to the perturbation of a submoon, it's extremely small and cannot be measured. So essentially the signal that is, the signal The total signal, including the contribution of the submoon, is not that different from the total signal that does not include the contribution of the submoon. So for this case, the contribution of the submoon is quite negligible. We have a similar situation with the transit method. We also did more simulations to determine the light curve of that this system would replicate in 4 different epochs. And we use Batman and we use Rebound for this. Because the distance between the moon and the submoon is smaller, way smaller, significantly smaller than the planetary radius, if the moon is orbiting, the submoon will always orbit. But now our question is, will the dim in light be significant enough to identify the presence of that submoon? And we determine it's not. We can definitely identify the presence of an exomoon, but we cannot determine the presence of a submoon because they would be too small and the transit depth could be confused with photometric noise. So far, no luck detecting the presence of submoons, but definitely we are able to detect the presence of an exomoon. And finally, we evaluate the possibility of submoons contributing to a radio emission produced by a similar mechanism of that between Io and Jupiter. Specifically, for the exomoon itself, for K1625bi, we find a total power of 3.2 gigawatts is possible for emission. And that is in the best case scenario. In the inner limit, these emissions will change depending on how close or how far the moon is from the planet. In the inner limit, we find the emission can be as high as 150 gigawatts. So again, there is most definitely a possibility of this Neptune-like moon producing a radio emission from its interaction with its host planet, more specifically, the magnetic field, electromagnetic field of the host planet. However, the highest expected flux, given the distance that this system is at, is way smaller than that of Jupiter. And that is the biggest challenge with this detection method, is the intensity of the signal decays as the radius, the squared of the distance, the radius squared of the distance. And so the further away it is, the harder it is to determine it. But ideally, our dynamical studies will help us try to predict when an L or an S burst could occur. And so what this means is that this intensity is boosted, and perhaps these could be observable from a larger distance. Now, when it came time to evaluate whether this submoon could contribute, we noticed that no, it is way too small to contribute to emission. And again, its contribution is essentially none, not just negligible, it's essentially none. So summarizing this first work, we performed n-body simulations of the Exomoon candidate system proposed by Tichy under Keeping. And we did 10 to the 5 planetary orbits using 20 random initial phases to determine the stability limits for both moon and submoons. Our motivation has to do with observational goals, but more specifically, we had noticed that no one had done this varying these initial phases. And not just that, my collaborator had proved in previous works that these initial phases have a say in the orbital stability of exoplanets. So why wouldn't it have one on the orbital stability of exomoons? We find that the limit for exomoons is 40% of the Hill radius of the planet, and for submoons is 33% of the Hill radius of its host satellite. We assumed circular coplanar orbits. Moreover, we explored detectability with RVs, transits, and radio emissions. Exomoons are generally detectable through most methods, but submoons essentially have negligible effects as perturbers in these emissions. So I will use the last couple of minutes to talk about some applications after we derived, or after I derived these constraints, these stability constraints. Some of these applications were done in a following paper on the same year. This was a letter, and it was put forward by my collaborator, Billy Quarles, where he took 6 KOI systems that were put forward as possible hosts for exomoons by Fox and Wiegert in the same year. And he utilized my expression of the critical semimajor axis to assess the orbital stability of these 6 systems. More specifically, what we have in the right panel, or all of the panels, are each of these systems that were proposed to be host for exomoons due to their TTVs. And in black, we have the stability region determined by my expression. In gray, we have the uncertainties of this stability region. And this uncertainty has a lot to do with observational uncertainties themselves, because these systems do have a very specific semimajor axis, very well determined, but the masses are not that well determined. They really rely on statistical relationships from Kepler data, and that is why we have such a wide uncertainty for some of these. And then the red line is essentially where my constraint lies. The constraint of the expression that we derived lies. For one of the systems, for most of the systems, the inner boundary, what I would like to call the stability inner boundary, it's usually for me the Roche limit, or maybe a little bit further away from the Roche limit. So for most of the systems, that Roche limit lies closer to the planet, closer than 2 planetary radii. But for one of the systems, the Roche limit is bigger than 2 planetary radii, and that's why we included it here. So essentially, we have the outer boundary, which is what Billy or Dr. Quarles calculated with my stability limit. And then we have an inner boundary, which is what we consider the Roche limit. Moreover, following up, moreover, in this work, in this collaboration with Dr. Quarles, he applied tidal constraints from Sasaki et al. 2012 to evaluate satellite migration into regimes. Those regimes are tidally moving inward, such that these moons reach the Roche limit and are disintegrated, or tidally moving outward outside of the Hill radius in the sense where these are ejected from the system. So Dr. Quarles wanted to evaluate that in a more thorough way than we did in the previous paper. And so combining both theoretical constraints, the one that we derived in my paper, and the one based on Sasaki et al., we found that 4 of the candidate systems are constrained due to tidal migration timescales. Therefore, they could not host exomoons. And we find that the other 2 could allow for low mass exomoons that are really closed in. So here we see an application where we can use the expression for critical semi-major axis that I derived to assess the candidacy of observed exomoons. And with this, I like to finish. It's a lot of information, but I would like to thank you for your time and for inviting me. I would also like to thank Dr. Billy Quarles, who is my collaborator, the NRAO Reber Fellowship, and my advisors here, UTA's Exoplanet Group, and my advisor at UTA, and the UTA LSAM program, which has funded a bunch of this research. And with that, please let me know if you have any questions.
Okay, Marialis, thanks very much. Very nice and clear presentation. So now we are open for questions. Anybody would like to make a question or comment?
Hey, hi, Otton. I would like to make a question.
So please, Ricardo.
Okay, Marialis, first of all, thank you for the presentation. Very good. Could you explain better the differences between your work and Domingo's work? Like the difference between the limits you both found?
Absolutely. Well, first off, Domingo's was a bit more thorough because they consider retrograde orbits, and I don't. That's the first one. And the second is there is no variation of the trajectories of this moon. There is no variation in the initial mean anomaly or the mean motion, and we do vary that given recent work by my collaborator, Billy. Honestly, when we started this work, we were only focused on submoons. Like, could submoons exist? Could they hold stable orbits? And that took a while to figure out. And as we were figuring that out, we realized we were just using Domingo's. We were just using their expression, and we were just going to use that. We never intended to improve on it or change it. But then we realized, oh, my collaborator told me, hey, I did this previous work, and if we vary these mean motions and these phases, if we consider more than just one trajectory, this can change, because I did this for exoplanets. And that's when I decided, okay, let's vary that too and see how it differs from what Domingo's found. So that's kind of how it came to be. And that's the main difference, is considering this 20 different initial phases at random.
Okay, yeah, very nice. Also, I have another question. I don't know if you heard about the IO exomoon candidate proposed by OSAS.
No.
Well, yeah, it's not like new. I think it's from last year. He found some prints and some prints of sodium and potassium coming out of the host planet, and he kind of said that Neo-like satellite could be the one producing this kind of effect. And I would just ask if you test your method there, but probably not.
Actually, I think I know what you mean. Is this okay? I know there was a recent work where they do talk about potassium, and is it sodium?
Yes, sodium and potassium.
So the abundance of that could be an indicator of volcanic activity.
Yes, exactly.
Right. So I've definitely read it. I've thought about it. I'm not sure if that constitutes a candidate, though. I think
no, it doesn't.
Correct. I think we would need more than that for a candidate, but it would be a good thing to add for candidacy criterion. Definitely, I think what's happening right now with exoplanetary science is that we're pushing the limits. What's happening also right now with astronomy is we need to expand to different wavelengths. I'm a firm believer that expanding to different wavelengths will reveal, hopefully, the presence of exomoons in planetary systems. And so different types of observations will reveal different aspects of these systems, and definitely including a spectral component to this would help us identify volcanic moons better. However, I would like to clarify that for the detection method that I'm after, a volcanic moon is not necessary.
Okay.
What we need is a conductive moon. So this type of interaction could very well happen with a moon that is ice, and that would conduct these currents. Definitely, we would need an environment that would conduct that, and it's better facilitated by volcanic moons. But even with stellar winds, as they travel, they could interact with a planet's magnetic field and an ice moon, and this same radio emission could be produced, because we do see these radio emissions in other planets in our solar system, but just way dimmer than Jupiter Io.
Okay, thank you.
Absolutely.
Okay, thanks, Ricardo. Anybody else would like to make a question or comment?
Awesome. Sorry, I was just going to say that someone in the chat.
Yeah, I think there's a question in the chat. Can you read? Marialis would like me to read. It's from Elielson. He has a problem on to
okay,
say.
So how could a submoon be formed? Oh, that's a great question. That's an interesting question. I think, we have three main formation mechanisms for satellites. I would think, in situ formation from a disk, which I actually think Ricardo has addressed. It's a great paper that actually came out about the same time mine did. It could be in situ formation. Well, he didn't address it for submoons. He addressed it for Kepler 1625 bi, but it was a great paper. And I would think that it could happen at a smaller scale. Why not? There is also impact formation, and there is also capture. To be honest, I haven't done enough studies to favor either one. I'm open to read more about how submoons could be formed. But yeah, again, submoons is kind of like a topic that's in its infancy. And so there aren't many works on submoons and their origins. So it'd be nice to read something about that, or addressing those three possible formation mechanisms.
Okay, good. Thank you. Anybody else? Well, I have a comment and a question. Could you show again?
Elielson has a question.
Who? Sorry?
Elielson.
I think it was made already. It was the one she answered now.
No, it's a different question.
Oh. Okay, so there's another one. Sorry. Okay.
Oh, okay. What's the typical tidal love number for a brown dwarf? I imagine a system composed by a star, a brown dwarf, and a satellite. Huh. Okay. Off the top of my head, I don't remember what the typical love numbers for any objects are. But I would assume there is this discussion where, what is a brown dwarf? I'm sure many of you are familiar with it, where is it really like a Jupiter, or is it more like a star, etc.? There is this discussion going on. I would think that if you were interested in assessing a system with a brown dwarf around a star, you could assume parameters that are Jupiter-like. I would think that. But I honestly don't have a specific answer or a number, but I could definitely get back to you on that in the future. I'm gonna write down your name. Soares Pereira. Okay. Are there any more questions?
Okay.
Oh, according to Beaumont, the typical, thank you, Ricardo. According to Beaumont et al., 2015, the typical tidal love number for a brown dwarf varies from 0.379 to 0.3. So.
Okay, good. So, anybody else? So I have a question and a comment. So could you put your presentation again and show that plot where you found the submoon limits from the dynamical, one of the first plots of your paper.
Oh. There we are. Oops. Can you see it?
No, it's not sharing. It's not.
I'm sorry. Let me try again.
Okay, it's coming. We have the screen.
There we are. So you were interested in?
It's not sure. Oh, okay, now it's good. Where you found these limits, the plot A versus E.
Oops, went too fast. Okay, yes.
Yeah, well, first a comment, and I'd like to see if you agree with me or not. In the top plot for the Exomoon, you explaining the difference of your work, where you selected, for instance, different longitudes, 20 random longitudes for each point here in this plot. And my question is, what the line you fit here is, let's say, to be sure that everybody, or let's say statistically saying, everybody below this line is stable. But the work of Domingos, they just considered zero value for the longitude. And so the yellow dots that cross the dotted line, the yellow squares that cross the dotted line probably were those that were close to zero, the longitude.
Mm-hmm.
So what I'm saying is that your limit is valid for any longitude, or let's say statistically valid for any longitude.
Mm-hmm.
But you may have the Domingos limit is valid for specific values of longitude. Do you agree with that? Do you agree with that?
Absolutely, I agree.
Okay, okay.
That is where the difference in initial mean motion takes place. My limit is based on where everything is stable regardless of the initial mean motion.
Okay.
Where we have a couple outliers, right? Where the mean motion will vary depending on the Hill radius of the fraction of the Hill radius. And so some of them will be favored as well. And so again, it's not at all invalidating Domingo's work. It's saying if I consider different trajectories, regardless of the trajectory that I considered, this is the limit. Whereas Domingo's limit is considering one trajectory.
Specific one, yeah, that's right. Okay, okay, good, good. We agree. So in the bottom plot, my question is, you write something in your paper, but you didn't comment much on that today. The structure you have on the stable region, for instance, that instability you have inside below the line. What can you say more about that?
You mean these values, right? For the
submoon around the semimajor axis 20.28, I think, something like that.
Right. You know.
Oh boy. I think she fell down. Okay, let's wait a little bit to see if she comes back. Okay, good idea, Ricardo. I think we can speak Portuguese now. I don't think we have anybody that does not understand Portuguese at the moment. Bom, a gente poderia então aproveitar, seguindo a sugestão do Ricardo, né? Acho que a Maria... Oh, hi.
Hi, I'm really sorry.
Okay, no problem.
I'm in New Mexico. We have thunderstorms. Our summer arrives, and we're in that transition between spring and
I
summer.
see.
And I run out of internet.
Okay.
It happens all the time. As
I
I
think
was saying,
you can just say you does not need to show again.
sure. As I was saying, we were also surprised to see this when we got the results of our simulations. I kind of mentioned the possibility of maybe some resonances.
Yeah.
But it's really something we don't dive deep into because although we have ideas of what it could be, we didn't do follow-up simulations to provide evidence of what it is. And we are hoping actually that in the future, someone who might be interested in submoons can explore that region more.
Okay. We can do that here. That's why I am asking you, because I'd like to know if you are doing that already or not. So.
You know, there are so many things I would love to continue doing in dynamics, but right now my observational work, it's taking the bulk of my time.
I see.
Really cool to read something about that, and you know, I'm very open to collaborations and to help in anything I can.
Okay, good. Perhaps we can do something about that. Good. That's great. Okay. Let's see. Do we have anybody else who would like to make any comment or question? So Marialis, thanks again. It was great to listen to you. Seems very nice to talk to you and to see you explaining your research. So, and just before we finish, I don't know if you'd like to say something. We have a few comments after your presentation. Would you like to say something?
Well, not really. Just thank you so much for having me here. I am very glad to talk to, again, a group of dynamicists and planetary scientists. This is very exciting for me. And just, I'm looking forward to see more work from your group. I've definitely read a bunch of papers from your group, and you guys are putting out great work, and please continue to do that.
Okay, thank you very much.
Thanks.
So now just before we finish our meeting, we usually have